Right now, the average lithium-ion battery pack costs about $108 per kilowatt hour. For a standard electric vehicle, that makes the battery the single most expensive physical component in the entire car. Building these power cells requires a highly specific mix of critical minerals. You need lithium to move the charge, cobalt to stabilize it, nickel to boost the energy density, and graphite to hold the power in place. Getting that lithium out of the earth is an incredibly water-intensive process. Miners pump millions of gallons of underground brine into massive surface pools, waiting for the desert sun to evaporate the liquid and leave behind the lithium salts. It places intense pressure on local, often arid water supplies. Extracting the other materials can be just as demanding on the physical landscape. Digging for cobalt and nickel relies heavily on deep, terraced, open-pit mines that carve immense craters into the earth and require massive industrial machinery. Moving millions of tons of rock and water carries a heavy environmental and financial toll. But pulling these raw minerals out of the ground isn't actually what causes the battery market to be monopolized, nor is it the primary reason prices stay so high. The real bottleneck in the electric vehicle revolution happens after the rocks are dug up. Raw dirt has to be chemically refined into highly purified, battery-grade materials before it can be used. If we look at this data visualization comparing global refining capacities, one country completely dominates the output. China currently refines 65% of the world's lithium and 74% of its cobalt. The rest of the world combined produces only a fraction of those volumes. Backed by this concentrated national refining capability, two immense corporate entities have emerged to lead the battery sector: BYD and CATL, whose headquarters we see. By controlling every step from chemical processing to final cell assembly, these companies have vertically integrated their supply chains. This efficiency has driven their domestic production costs down to an industry-low $84 per kilowatt hour, securing them a massive 72.2% share of the global market. Competing automakers and Western nations cannot quickly replicate decades of heavy refining infrastructure. To survive, they have to seek structural advantages entirely outside the mine, looking instead to radical innovations on the factory floor. Traditional battery manufacturing uses a highly automated, rapidly moving assembly line built around what is known as the wet slurry process. It takes about 10 distinct steps to build a battery. Powders are mixed into wet paste, coated onto thin metal foils, compressed through heavy rollers, cut, stacked, filled with liquid electrolyte, and sealed into a modular pack. This chart breaks down the total energy required to run the factory, and one phase stands out. The wet slurry relies on chemical solvents that must be baked off. Drying consumes nearly half of the facility's total energy. Engineers are replacing this liquid-heavy step with a breakthrough technique called the dry electrode method. Instead of a wet paste, materials are mixed with a dry binder called fibrillized PTFE, holding the powder together without solvent. Removing those massive drying ovens physically shrinks the footprint of the factory and drops overall energy consumption by 40%. Cutting the energy bill makes battery manufacturing significantly cheaper. More importantly, eliminating liquid solvents creates the exact economic and environmental conditions required to manufacture next-generation battery chemistries. For years, the premium industry standard has been NMC, a chemistry relying on nickel, manganese, and cobalt. It offers excellent energy density, easily pushing vehicles past 300 miles of range, but it requires that highly contested, expensive cobalt. Comparing NMC against lithium iron phosphate, or LFP. While NMC is costly, LFP drops the price to $81 per kilowatt hour and lasts significantly longer, delivering up to 5,000 cycles. Eliminating cobalt drops fire risks to near zero, but sacrifices cold weather reliability and range. Beyond LFP, automakers are already looking ahead. We are seeing major presentations, like this one from Toyota, gearing up for solid-state batteries. These batteries promise ultra-dense power without liquid electrolytes, while other companies pursue sodium-ion cells for cheap, lithium-free city transit. Choosing the chemical makeup of a battery is no longer strictly an engineering decision about range. Automakers are deliberately selecting chemistries like LFP to bypass the most concentrated materials, designing their way out of supply chain monopolies. Of course, large battery packs aren't the only way to power a vehicle. Hydrogen fuel cells and hybrid drivetrains offer entirely different mechanical paths that reduce or bypass our reliance on heavy critical minerals. But for the millions of pure electric vehicles already on the road, the battery hardware has a finite lifespan. After a decade or two, these cells slowly lose their internal charge, eventually degrading below 80% of their original capacity, at which point they are no longer viable for highway driving. That doesn't mean the hardware is useless. In the second life market, degraded modules, like these stacked green units, are culled from cars and wired together into stationary storage racks, acting as massive backups to stabilize local power grids. Squeezing another 10 years of utility out of an old pack keeps toxic waste out of landfills. Yet, eventually, those cells will completely die, and the highly valuable metals trapped inside will need to be reclaimed. At the absolute end of their lifespan, dead batteries go through advanced hydrometallurgy and direct recycling. Recyclers shred the packs and use chemical baths to strip away the plastics, reducing the internal components to a concentrated powdery substance known as black mass. The black mass is further refined. Modern recycling recovers up to 98% of critical metals, separating pure lithium, cobalt, and nickel. Because these metals are identical to mined ore, they ship directly back to the factory floor, closing the entire supply chain loop. When you combine a highly efficient closed recycling loop with cobalt-free chemistries like LFP, the geographic grip of any single nation begins to slip. Automakers can source their future materials from the batteries they've already built. The supply chains that power the next century of transportation won't necessarily start in a distant desert or an open-pit mine. The most valuable mineral reserves of the future will be the millions of electric cars already driving through our cities today.